My name is Philip Dale. I work in the physics department of the university. I investigate the properties of solar cells. These are devices which convert energy from the sun, so light, into electrical energy. The new part is that we try and make them from materials which are earth abundant. That means that we can find the materials all over the world, and the elements we commonly work with now are copper, zinc and tin, and these can be found all over the planet. Research in solar technology is actually focused in many different domains. There are no yet set winners. So we have people working on organic solar cells, we have people still working in silicon solar cells, and there's still people like us working in thin film technology. We, of course, consider thin film technology to be the superior technology and will be the one that leads to the market winner in the end. What we're currently trying to do is improve the device efficiency. Currently, the world record with our technology is at 11%, but we need to get to 15 or 20% before it becomes commercially viable. I was the first Attract Fellow, and during that time, I've had the ability to apply for other research projects, so to extend the work started in the Attract program and really take it to the next level.
My name is Andreas Michels, and I'm an Attract Fellow. The title of the Attract project is Rare Earth Nanomagnetism. The term rare earth basically refers to a group of elements. These are mostly metals, and for the synthesis of good permanent magnetic material, one does need these materials. You cannot have a good permanent magnet without these materials. These rare earth magnets, they have a multitude of applications. You can find them, for instance, in magnetic resonance imaging. You can find them in hybrid electric vehicles, or a very popular field of application is in generators in wind turbines. We mainly focus on microstructure property relations in these magnetic materials, and the features of this microstructure, for instance, the particle size, the crystallite size, has an impact on the magnetic properties. We can vary the crystallite size and then study its effect on the magnetism. And in this way, we aim to optimize the magnetic properties. What I can definitely say is that the Attract program certainly helps to really become an independent researcher. The amount of 1.5 million euros for a period of 5 years is, on an international level, very competitive.
So I'm Massimiliano Esposito, and I'm an Attract Fellow. So I received a significant amount of money to carry on a project on the stochastic thermodynamics description of small systems here in Luxembourg. In physics, thermodynamics is really one of the pillars. And if you try to apply thermodynamics to small systems, you will have to face the fact that small systems fluctuate very strongly. You have to deal with the fact that small systems can be very strongly perturbed, and so they usually operate far from equilibrium. And third, you might have to deal with the fact that there are quantum effects, in particular at low temperature, that you may have to deal with. So we can use this thermodynamic theory that we developed to understand why nature has succeeded in being so efficient and operating so efficiently at this very small scale, far from equilibrium, highly fluctuating environment, to learn what are the key ingredients. And once we know what are these key ingredients, we can reproduce them in artificial devices. The quality of life is high here, but the main reason is the scientific opportunity, yes. The fact that by coming here, I would be in conditions that I would not get in most places in Europe.